In this videotape, we're going to simplify algebraic expressions involving radicals. We'll solve some radical equations and do a little work with complex numbers. In the problems that I'm going to be giving you, I want you to perform the indicated operations and express your answers in simplest radical form. I also want you to assume that all variables represent positive numbers. So in the examples that we're going to be doing throughout this tape, I want you to perform the operations and express your answers in simplest radical form and assume that all variables represent positive numbers. Okay, the only term you might have some difficulty with here is simplest radical form, so let's go over that idea. When I say simplest radical form, there are three basic properties of simplest radical form. First of all, you want to take as much as you can out from under the radical sign to simplify. You want no fractions left under the radical and no radicals in the denominator of a fraction. Okay, so these three basic properties are what we mean when we say simplest radical form. Take as much as you can out from under the radical sign. No fraction should be left under a radical, and there should be no radicals in the denominator of a fraction. Okay, let's get started. In the first example, we want to simplify the square root of 27 x to the 4th y to the 9th. Okay, we want to take as much as we can out from under the radical. Since this is a square root problem, we are looking for perfect square factors of 27x to the 4th y to the 9th. And what I'm going to do is to rewrite this as the square root of, I'm going to factor this, a perfect square, all the perfect square factors first, and then whatever's left. So, for 27, the greatest perfect square in 27 is 9. So 27 I'll write as 9 times 3. X to the 4th is a perfect square. And y to the 9th I'm going to write as y to the 8th times y. This is 27 x to the 4th y to the 9th, but it's written as a perfect square factor times something which is not a perfect square. Now the square root of a product is the product of the square roots of the individual factors. So it'll be the square root of 9x to the 4th y to the 8th times the square root of 3y. Now, the first factor here was a perfect square, and therefore we will be able to write this without the radical sign. The square root of 9, that's 3. The square root of x to the 4th is x squared. The square root of y to the 8th is y to the 4th. We take the square root of the 9, and we have the powers. Okay, x squared y to the 4th. So we have 3x squared y to the 4th times the square root of 3y. This is now in simplest radical form. We've taken out as much as we can from under the radical sign. There are no fractions under the radical sign, and of course no radicals in the denominator. Now, what if the problem had been, instead of the square root of 27x to the 4th y to the 9th, what about the cube root of 27x to the 4th y to the 9th? Our goal is still simplest radical form. However, now instead of looking for perfect square factors of this expression, we are looking for perfect cube factors. Okay, so I'm going to write this as the cube root of now 27 happens to be a perfect cube, so I'll put the 27 in the perfect cube portion. X to the 4th I'm going to rewrite as x cubed times x, because x cubed is a perfect cube. And y to the 9th happens to be a perfect cube already. So this is still 27x to the 4th y to the 9th, but we have refactored it, this time pulling out perfect cube factors in front. Now, the cube root of this product is the product of the cube roots of the individual factors. So it'll be the cube root of 27 x cubed y to the 9th times the cube root of x. The cube root of 27, that's 3. The cube root of x cubed is x. And the cube root of y to the 9th is y to the 3rd times the cube root of x. So here we get 3xy cubed times the cube root of x. Just like over here, we took the square root of the constants and we halved the powers of the variables to get square roots. Here we took the cube root of the constant and we took a third of the powers of the variables to get the cube root. We started with the same expression under the radical in both cases. You have to pay careful attention to what the index is. This was a cube root. When you see nothing in here, there is a 2 implied. In other words, a square root. Okay? The same problem by changing this 2 to a 3 is done completely differently. All right, problem number 3. We want to simplify this. The square root of 9x to the 16th plus 16x to the 16th. Now, while the square root of a product is just the product of the square roots of the factors, you cannot do something similarly with sums. You cannot say the square root of a sum is the sum of the square roots. You can say the square root of 9x to the 16th plus the square root of 16x to the 16th. That you cannot do. It works for products, but not for sums. So instead, you have to simplify this by adding the like terms. 9x to the 16th plus 16x to the 16th gives us 25x to the 16th. And now, take the square root of 25 and the square root of x to the 16th. Now, while you take the square root of the numerical constant here, you have the power. So the answer is 5x to the 8th, not 5x to the 4th. Some people get all excited. They take the square root of 25 and they take the square root of 16. No, it's the square root of 25, and the square root of x to the 16th is x to the 8th. Because remember, x to the 8th times x to the 8th is x to the 16th. So the square root of x to the 16th is x to the 8th, not x to the 4th. Okay, problem number 4. The cube root of 16 x squared y times the cube root of 4x. Sometimes, in order to put a problem into simplest radical form, you have to first sort of complicate it. The cube root of this times the cube root of that, I am first going to make it the cube root of the product. 16 times 4, that's 64. X squared times x, that's x cubed, y. So I'm rewriting it as the cube root of 64 x cubed y. Now, I will redo this by writing this as the cube root of 64x cubed, which is a perfect cube factor, times the cube root of y. Now the cube root of 64x cubed, the cube root of 64 is 4, the cube root of x cubed is x, and then that's the cube root of y. So we get 4x times the cube root of y. And we would not have been able to get that unless we first multiplied these two expressions together and then worked with the whole thing. So 4x times the cube root of y. Problem number 5. The square root of 128 over the square root of 18. Okay, this is not in simplest radical form. Let's see what we can do. Well, let's take our perfect square factors. The square root of 128 is the square root of 64 times the square root of 2. The square root of 18 is the square root of 9 times the square root of 2. We can divide numerator and denominator by the square root of 2. We get the square root of 64 over the square root of 9, and they both happen to be perfect squares under the radical, so we get 8/3 as our answer. Problem number 6. The square root of 3/5. We have a fraction under the radical sign. The first thing we do is to take the square root of the numerator, divide by the square root of the denominator. But now we have a radical in the denominator, so it's not in simplest radical form. What we do is we multiply numerator and denominator by something so as to eliminate the radical in the denominator. And in this case, what we need to do is to multiply numerator and denominator by the square root of 5. We get an equivalent fraction because we are multiplying numerator and denominator by the same quantity. Now, the square root of 3 times the square root of 5 is the square root of 15. The square root of 5 times the square root of 5 is 5. And this is now in simplest radical form. There are no perfect square factors that we could take out here. So we've taken as much as we can out from under the radical sign. There are no fractions under the radical. There are no radicals in the denominator. In problem number 7, we have the following. The cube root of 27 over 25. We have a fraction under the radical sign. So we'll take the cube root of the numerator, divide by the cube root of the denominator. Now, once again, we have to get rid of the radical in the denominator, so we have to multiply top and bottom by something so that we eliminate that radical. Now, in the preceding problem, when we had the square root of 5 downstairs, we multiplied by the square root of 5, because the square root of 5 times the square root of 5, the square root of 25 is just 5. Here we need to multiply by something so that we get a perfect cube under the radical, and then we can take the cube root of it. Okay, so what we're going to do is multiply top and bottom. You can't multiply by the cube root of 25. That won't help us. We're going to multiply top and bottom by the cube root of 5. Let's see why. On the bottom now, we'll have the cube root of 25 times the cube root of 5, which is the cube root of 125. Now, 125 happens to be a perfect cube. On the top, we have the cube root of 27. Well, the cube root of 27 happens to be 3 times the cube root of 5. So we get 3 times the cube root of 5 over the cube root of 125, which is 5. So 3/5 times the cube root of 5. For our next problem, we'll do the following. xy times the square root of 5xy times 4y times the square root of x over the square root of 9y cubed. We want to put this into simplest radical form. Okay, first let's see what's going on here. Outside of the radical, we have x times y times 4 times y, or 4xy squared. The xy times the 4y gave us 4xy squared. The square root of 5xy, the square root of x. If you multiply the square root of 5xy times the square root of x, you get the square root of 5x squared y over the square root of 9y cubed. Now, let's see how much we can pull out from under the radical. 4xy squared. I'm going to write this as the square root of x squared times the square root of 5y. And downstairs, I'm going to write this as the square root of 9y squared times the square root of y. Each case, I'm looking to pull out the perfect square factors. 5x squared y, x squared was a perfect square factor. 9y cubed, 9y squared was a perfect square factor. Okay, let's see what we have now. We have 4x y squared. Now the square root of x squared is just x. We assumed all variables here are positive. And then that's the square root of 5y. And over here, the square root of 9y squared is 3y. That's a perfect square times the square root of y. Okay. Now, we still don't have simplest radical form because we have a radical in the denominator. If we want to get rid of this radical in the denominator, we'd have to multiply numerator and denominator by the square root of y. And let's see what happens. We will get, let's continue up here, 4x squared y squared the square root of 5y times the square root of y is the square root of 5y squared divided by 3y, the square root of y times the square root of y. 3y times y. The square root of y times the square root of y is y, so 3y squared. Okay? This is 4x squared y squared. The square root of 5 times the square root of y squared over 3y squared. We can divide numerator and denominator by y squared. The square root of y squared is just y, and we get here, for our final answer, 4 times, let's put the constants first, 4 times the square root of 5, x squared y over 3. 4 times the square root of 5, x squared y over 3. The y squareds canceled. 4 times the square root of 5, x squared times y over 3. Let's go over the problem from the beginning. We wanted to express this in simplest radical form. The first thing we did was to multiply these two radicals together. The square root of a times the square root of b is the square root of ab. Then we looked for perfect square factors in the numerator and the denominator. We pulled out the square root of x squared here and the square root of 9y squared here. Square root of x squared was just x. The square root of 9y squared was 3y. So that got us to this point. However, we still had a radical in the denominator, so we had to multiply numerator and denominator by the square root of y. And then proceeding in this manner here, we got 4x squared y squared times the square root of 5y squared, 3y times y. The square root of y times the square root of y was y. So we had 4x squared y squared times the square root of 5y squared, which we wrote as the square root of 5 times the square root of y squared over 3y squared. The y squareds canceled, leaving us this for the final answer. All right, for our next problem, simplify the following. Minus the square root of 12 plus 5 times the square root of 27 plus the square root of 48. Now, we can only combine radicals if they have exactly the same expression under the radical sign. Okay, so at first glance, it might look like you can't simplify. However, you don't determine whether or not you can combine radicals until you first put each of the radicals into simplest radical form. So what we have to do is first pull out as much as we can from under the radical sign. So we're going to write, in each case, look for perfect square factors. So 12 is really 4 times 3. 27 is 9 times 3. And 48 is 16 times 3. And then we begin to see that we probably will be able to simplify this problem. Minus, now, the square root of 4 times the square root of 3, plus 5 times the square root of 9 times the square root of 3, plus the square root of 16 times the square root of 3. That gives us minus 2 times the square root of 3, plus 5 times 3, that's 15 times the square root of 3, plus 4 times the square root of 3. So now we do have the same expression under the radical in each case. So we can combine the radicals and we get 15 plus 4, 19, minus 2, 17 times the square root of 3 as our answer. But you would not be able to see that until you first put each of the radicals into simplest radical form. In our next problem, we want to simplify the following. The square root of 40 minus 3 times the square root of 2/5. All right, we want to put them into simplest radical form. The square root of 40 is the square root of 4 times the square root of 10, pulling out a perfect square factor. Minus 3 times, now we don't want any fractions under the radical sign, so we'll make it the square root of 2 over the square root of 5. However, we also don't want any radicals in the denominator, so let's see what we can do. We have the square root of 4, that's 2 times the square root of 10, minus 3 times the square root of 2 over the square root of 5. In this second term here, we have to multiply by something, top and bottom, so that we will eliminate the radical in the denominator here. We want to rationalize the denominator. We will multiply top and bottom by the square root of 5. So we'll get 2 times the square root of 10 minus 3 times the square root of 2 times the square root of 5, which is the square root of 10, over the square root of 5 times the square root of 5, which is just 5. 2 times the square root of 10 minus 3 times the square root of 10 over 5. Now, if we would like to combine further, we have fractions to combine over into one fraction. We need the same denominator. So I'm going to first rewrite them. It's two fractions having the same denominator. The lowest common denominator is 5. The second fraction already has that denominator. The first one can have that denominator if we multiply the bottom by 5, and of course we have to multiply the top by 5 as well. So multiplying the bottom by 5 and the top by 5, that gives me 2 times 5, 10 times the square root of 10. We now have two fractions with the same denominator. We combine the numerators. 10 the square root of 10 minus 3 the square root of 10, that gives us 7 the square root of 10 over 5. Combine the numerators. It's like 10a minus 3a, that's 7a over 5. 7/5 the square root of 10, or 7 the square root of 10 over 5. Problem 11. We want to simplify the following. The square root of 8 divided by the square root of 8 minus 2. We want to put this into simplest radical form. However, we have a radical in the denominator. We can't simply say I'll multiply top and bottom by the square root of 8, because when you multiply the bottom by the square root of 8 times the square root of 8 gives you 8, but then minus 2 times the square root of 8. So it'll just reappear in the second term instead of the first. Okay, so what we need to do is to multiply top and bottom by some quantity so that there is no longer a radical in the denominator. Well, if you remember that a minus b times a plus b is a squared minus b squared. Right, by first outer inner last FOIL, you get a squared plus ab minus ab. They cancel out, minus b squared. If you think of this as a minus b, and if you multiply top and bottom by a plus b, in other words, the square root of 8 plus 2, and you have to do the same thing on the top. This is like a minus b times a plus b. This will give us downstairs a squared minus b squared. A minus b times a plus b should be a squared minus b squared, this squared, which will be 8, minus this squared, which will be 4. Upstairs we'll have the square root of 8 times the square root of 8 plus 2, but downstairs we will no longer have a radical. Okay, let's look at this. A minus b times a plus b is a squared minus b squared. This squares out to 8 minus this squares out to 4. Okay, let's see what we have. Downstairs, 8 minus 4 is just 4. Upstairs, the square root of 8 times the square root of 8 is 8, plus the square root of 8 times 2 is 2 times the square root of 8. Well, to have simplest radical form, not only can't you have a radical in the denominator, but you have to take as much as you can out from under the radical. The square root of 8 is really the square root of 4 times the square root of 2. So we get here 8 plus 2 times the square root of 4 times the square root of 2. The square root of 4 is 2. 2 times 2, that's 4. 8 plus 4 times the square root of 2 over 4. You can factor out a 4 in the numerator. That's 4 times 2 plus the square root of 2 over 4. Because 4 times 2, that's 8. 4 times the square root of 2 gives you that. And now divide numerator and denominator by 4, giving us our final answer of 2 plus the square root of 2 for this problem. So in problem 11, you can put this into an equivalent form of 2 plus the square root of 2, which is in simplest radical form. In the next few problems, we're going to be dealing with radical equations, equations involving radicals. And in each case, we're going to want to solve for the variable. So in this problem, solve for x. We have the square root of x minus 1 plus 2 equals 4. To solve a radical equation, or an equation involving a radical, the trick is to isolate the radical. So we're going to subtract 2 from both sides. To get the radical alone, we'll have the square root of x minus 1 equals 2. Now, to then solve this equation, we have to take, well, we have square root of x minus 1 is 2. We have to square both sides of the equation. When you square the square root of x minus 1, you'll just get x minus 1 equals 2 squared, which is 4, leading us to an answer of x equals 5. We will then check our solution in the original equation. The square root of x minus 1 plus 2 equals 4. We get the square root of 5 minus 1 plus 2 should be equal to 4. The square root of 5 minus 1 is the square root of 4. The square root of 4 is 2. 2 plus 2 should be equal to 4, and of course 4 equals 4. So the solution is x equals 5. So the trick for solving a radical equation is to isolate the radical on one side. We accomplished that by subtracting 2 from both sides of the equation. The square root of x minus 1 was equal to 2. Squaring both sides, x minus 1 equals 4, and then solving for x equals 5 and checking our answer. The square root of 4, 2 plus 2 does equal 4. In our next problem, 13, the cube root of x minus 1 plus 2 equals 4. Once again, solve for x. Now you have to pay attention here. It's a radical. Of course, you want to isolate it on one side of the equation, as before. So we're going to subtract 2 from both sides. The cube root of x minus 1 equals 2. Now, in the preceding problem, we had the square root of x minus 1 is 2. And to solve for x, we had to square both sides. To undo the square root, we squared both sides. To undo a cube root, you have to cube both sides. So, you have to pay careful attention to what the index is there, to what number is in here. The cube root of x minus 1 cubed, that would be x minus 1, equals 2 cubed, or 8, giving us x equals 9 as our solution. And then checking in the original equation, the cube root of x minus 1 plus 2 equals 4. The cube root of 9 minus 1 plus 2 should be equal to 4. The cube root of 9 minus 1 is the cube root of 8. The cube root of 8 is 2, plus 2 should be equal to 4. And of course, that checks out. So x equals 9 is the solution. In problem 14, solve for x, the following. X to the 2/3 equals 16. All right? To solve this, to get x alone, I'm going to have to raise both sides to the appropriate power. I'm going to have to raise both sides to the 3/2 power, because x to the 2/3 to the 3/2 power will be x to the 2/3 times 3/2, or x to the 6/6, or x to the 1, will be equal to 16 to the 3/2. Now, 16 to the 3/2 means the square root of 16 cubed. It's also, by the way, equal to the square root of 16 cubed. In other words, it can be the square root of 16 quantity cubed, or the square root of 16 cubed. Now, I find it easier to write it this way. See, here you'd have to cube the 16, and then hope you recognize it as a perfect square if it is. Here, which is equivalent, we look for the square root of 16, which happens to be 4, cube that, and we get our answer of 64. And for our check, x to the 2/3 equals 16. 64 to the 2/3 should be equal to 16. The cube root of 64 squared should be equal to the 16. The cube root of 64, which is 4 squared, should be equal to 16. And of course, 16 checks out. Now, in the book, we learned that the real number system is not really enough for us, and we've also learned that there's such a thing as complex numbers. And in the following problems, I want you to express your answers in a plus bi form. Now, refreshing your memory, the square root of -1, which does not make sense in the real number system, is defined to be I. Okay? There is no real number whose square is -1. Okay? We have a complex number I. Now, I squared represents -1. I cubed is I squared times I. But I squared is minus 1 times I, so that's minus I. And I to the fourth is I squared times I squared, or minus 1 times minus 1, or plus 1. So the square root of minus 1, that's I squared is minus 1, I cubed is minus I to the fourth is plus 1. Now, using that as a basis, express in a plus bi form, problem 15, I to the 35th power. Now the idea is to find the biggest multiple of 4 that's contained in 35, because I to the fourth is plus 1, and we can use that to reduce the power here. So I'm going to write this as I to the 32 times I cubed. I to the 32 times I to the 3 is I to the 35. But I to the 32 was chosen because it was the largest multiple of 4 contained in 35. So we had, this is really I to the fourth to the 8th times I cubed. I to the 32nd is I to the fourth to the 8th. Now why do we want I to the fourth? Well, I to the fourth, if you remember, was plus 1. I to the fourth is plus 1. So this is plus 1 to the 8th times I cubed. Well, plus 1 to the 8th is just 1, so it's just I cubed. So I to the 35 power is the same as I to the third power, which is the same as minus I. So you could think of this as 0 minus 1I. If you wanted to write it in a plus bi form, minus I, or 0 minus 1I, a plus bi. The real part is 0 and then minus 1I. And for the last problem, let's try the following. Once again, express in a plus bi form the following: 2I plus 3 times I minus 5. We can multiply these the way we multiply binomials, using the FOIL method. First, outer, inner, last. First, 2I times I, 2I squared. Outer, 2I times minus 5, that's minus 10I. Inner, plus 3I. And last, minus 15. That gives us 2I squared minus 10I plus 3I, that's minus 7I, minus 15. Now we want to express this in a plus bi form. We have to remember that I squared is the same as minus 1. I squared is minus 1. So we have 2 times minus 1, minus 7I, minus 15. Minus 2, minus 7I, minus 15, or minus 17, minus 7I. It is now in a plus bi form. And that brings us to the end of this tape.